Dear students, welcome to the lecture series on the topic Engineering Graphics. Today we are going to discuss about Introduction to the section of the solids. I am Dr. IPS Ahuja, Professor, Department of Mechanical Engineering, Punjabi University, Patiala. Now the sectioning or the cutting of the solids is usually carried out in order to view the clearer picture of the interior details of the objects which are otherwise drawn as hidden lines or the dotted lines onto any given orthographic projection. So an object is difficult to visualize from its orthographic views if its internal structure happens to be complicated. So in such a case, the concept of sectioning of the object helps to interpret and visualize the object easily. So the object is assumed to be cut by an imaginary plane to reveal the internal details of the objects over there. So an imaginary plane which cuts the object is called a cutting plane or a section plane. So the new imaginary face which is generated on the object after the cutting or the sectioning has been done, it is called the section. Now this is the representation of the cutting plane in which you have got, it is a thick broken line that extends past the edge of the object and it is terminated with short 90-degree arrowheads over there. So here you can see this is the object. So the cutting plane, it will be represented by a thick broken line in which there are arrows which are shown towards the ends over there, and this cutting plane will be extending past the actual object whose section needs to be obtained over there. So here we can see that this is an object whose internal detail we want to evaluate, because you see otherwise if we draw the orthographic view of this object, this hollow portion over here will be shown with the help of a hidden line or a dotted line. Similarly, this is a hollow portion which is there. This is the top view of the object. This is the hollow portion which is there on the side wall of this particular component. So if we want to look into the deeper details of this particular object, now we can cut it through this particular cutting plane, and the arrows, they indicate that in which direction we are going to have the look at the given object over there. Because you see, while we were discussing the principles of the dimensioning, we discussed that never dimension the hidden lines over there. That is, whatever the interior details are there, usually we are not going to carry out the dimensioning over there. So if we have to have a clear understanding of the interior details of the object, then the only way we can look into the deeper details of the object or the interior details of the object will be to cut open the object in whichever way the greater details about the internal components, internal parts of the components will be visualized in a particular view. So if we are going to cut open this, you see this is our cutting plane, and the moment we cut open this, now you can see that this is the internal portion over here, and similarly it gives us a better idea about, that is, this is the niche which is made over here, which was not visible to us from the external orthographic view. Similarly, this was a dotted line and this was again indicating that there is a hole over here. Now through this sectioning we are able to get the exact view of the internal details of this particular object. And once the object has been cut, so at whichever portion it has been cut, this is called the section. So this is the cut portion or the section portion over there, and the section portion is shown with the help of the hatching lines over there, which will be thin lines, and these lines will be at an angle of 45 degree with respect to the reference line, that is the XY reference line onto which this particular projection is made. So these lines, hatching lines, will be thin lines, and these will be equi-spaced lines over there, right? So this is how we are going to carry out the sectioning or cutting of the objects so that the internal details of the objects, they can be visualized in a better way over there. Similarly, you can see here we have a circular component into which there used to be a hole over here. So from the external side, if I draw the orthographic projection, so corresponding to this hole, so in the front view I am going to get the rectangle made over here, which will be my front view projection, and then there will be two dotted lines which will be projected over here. Now if I want to have a proper description or the detail of the internal hole which is there into this particular object, now I can cut open this. So once again you can see this is the original solid, so this is my cutting plane, and the arrow indicates that this is the side from which I am going to look at this cut portion. So once I cut this open into two halves over there, now the remaining portion which will be left out, this will be called the section or the cut portion, and wherever the cross sections will be there, this is called the cut section. And then now whatever interior hole which was appearing to me in the front view as the dotted lines, now I will be able to see the dark lines or the object lines corresponding to this cut portion over there. Now I can carry out any sort of dimensioning also in the section view over there. Now there are number of ways in which the solids can be cut in order to have a clearer understanding or the clearer picture of the internal details of the components or the object. So the first method is called full section view. So in the full section view, we have the object available with us. Now we are going to cut this. Now our cutting plane will be lying over here, because if I draw the orthographic view, I am going to get a dotted line over here. I am going to get a dotted line, and then corresponding to the bolt length, again a dotted line will be there. So this is the bolt head where it will be situated, and corresponding to this bolt length over there, now I am going to get a dotted line. But I wanted to see the internal detail of this particular object over here. So in order to have a better feel about the internal detail, now what I have done, I have just managed to cut this object into two halves. So that is why we call it full section view. That is, the total component will be sectioned into two halves over there. So using a single cutting plane, I am going to obtain the internal details. Let us see how those details will be there. Just see, once again, these are my arrows over there. So the arrows will indicate that I am going to look at this portion. So this portion I am going to throw away. This is the cut portion. Now this is the portion which is going to reveal the internal details of the object over there. So I am looking from this side. That is why the observer is shown over here. And then you can see the internal portion. This is the called hatching over there. So this is my section portion. Now I can have a clearer image that where my bolt head is going to rest. This is where the shank of my bolt is going to go over there into the component. So this is how I can have a better understanding of the total details of the object. And usually we are going to carry out the sectioning to have better understanding of the internal details of the objects which are otherwise not visible clearly onto the orthographic views, because they are usually drawn with the help of the hidden lines over there. Similarly, you see another example of the full section view. Now here is one component where there is a hole over there. You can see the top portion. This is my top view of this component. So into the top view I can see through. There is a hole over here. Again in the top view, this component, again there is a hole over here into this wall. So now the clearer picture is not available because I cannot do the dimensioning over here corresponding to the hidden portion of this particular component. So if I want to have a clearer picture of this, now what I can do, you see this is my cutting plane which is again going to cut this through and through. So it will be passing through this point and this point, and it will be cutting this component through and through over here. That is why again we call it full section. Now once we cut it, I will be able to see this portion, because again in the orthographic projection I am going to get the dotted projections corresponding to this hole over there. Similarly, corresponding to this bottom hole also in the front view, the dotted projections will be there. And even in the top view corresponding to this hole, again the dotted projections, they are available over here. So I want to have better understanding of this internal details. So you see, I have managed to cut this object through and through at the center, while the observer is going to look at this object from this side. Now you can check, this is the wall of the object which is available. Now the internal detail corresponding to this hole, it is available to me through this sectioned view. Similarly, this hole in the farther wall of the component, it was not available to me in the front view over here. So now I can have the darker view or the object line view corresponding to this portion of the component over there. So this is another example of the full section view. Similarly, here again you can see this was my component. So I was not getting the proper feel of these holes over there, cross sections over there. So what I have done, I have managed to cut this object at the center over there. Since all these three holes, they are available in the same line over there, so the single plane would be sufficient to provide me the details. And in the subsequent discussion you will see that if these holes, they are not available in the single line, we can even have the cutting plane in the different orientation. That will be called offset section. So that we are going to discuss in a while. But here, since all these three holes, they were available in the straight line, so we have cut this section over here, cut this object at this particular point, and then you can see now I am able to get proper picture of the whatever internal details of this component were there at this particular cross section over here. Similarly, you can see there is another view. I want to have clearer picture of the internal detail of this particular component. So once again, I have managed to cut this. So here you can see there is a hole which is running through and through. So over here it appears as a circle, over here it will appear as a dotted line over here. But then the moment I cut it with the help of one cutting plane which will be passing through the center, so I am able to have a proper understanding of the internal details which otherwise are complicated and difficult to comprehend in all of the views, whether it is the front view or it is the top view. So this way again full section view is obtained in order to reveal the internal details of the object in a better way. So this is another example of full section view, where here at this juncture we have applied the cutting over there or the sectioning over there as the observer is looking from this end. Now you can see this is the cutting which has been obtained, and this web and all the other details, that is this hole etc., they can be visualized in the sectioned view over there. Now in many cases I want to develop proper understanding about the original drawing and the cut drawing over there, that is the section portion over there. So we are not cutting the component fully because I want to see to it that how would it look like if I am going to draw the unsectioned view. So here I am going to cut this object 50% only. You see my cutting plane is like this. So since my cutting plane is cutting this object 50%, so we call it half section view. So in the half section view, we can show the details which are otherwise available in the orthographic view and the details which are available in the section view. So in the orthographic view, you see, we are not able to see the interior portion. Obviously, we could have drawn the dotted lines over here. So one dotted line I could have drawn over here, two dotted lines corresponding to this hole we could have drawn. But again, the representation of the orthographic only shows me the outermost portion of this particular component. So the construction of this component is shown with the help of object lines. So the object lines, they do not provide me the flexibility to look at the interior details over there. So if I am going to provide more clarity, I could have drawn one dotted line over here and two dotted lines over here corresponding to this hole. But if I am going to show both of them side by side, so that is why I have avoided showing the dotted lines into the original orthographic view. So in the original orthographic view, I have shown the outermost portion, that is, this is what is visible, and in the section view what I can see, so this is the greater detail of the internal detail of the component which will be visible. So such sections which are cutting open 50% of the solid, So we call them half section views over there, so that we can compare the original view with the cut view. That is what detailing the sectioned view will offer. So those things we can compare. Over here once again also you can see this is a component. So I have cut it open 50%. That is one side, half side I have opened it. So once I open it half side, so you can see I am able to see the internal details corresponding to 50% of the solid, and remaining portion I'll see. If no sectioning is done, this is what is visible. If sectioning is done, this much internal details they will be revealed by the sectioned view. Then next you have the offset section, because in the previous case all these three holes they were lying in the same line. If they were all lying in the same line, single cutting plane would be sufficient to reveal the internal details of this particular object. But since these holes they are offset, so what we can do, we have the flexibility that now you can see we can manipulate our cutting plane in such a way that it will pass through different cross sections. Even though it is there in the horizontal direction only, but it will have flexibility to cover different segments of the object, so that in a single view I will be able to see this internal detail, this internal detail, and this internal detail of the object. So you see here the vertical reorientation is allowed over there. So that is why we call it offset. Otherwise in a single cutting plane I would have got one cutting plane for this, another cutting plane would have been required to reveal detail of this particular segment of the object. So one cutting plane would have described the details of these two holes, and another cutting plane would have required. But by carrying out this offset, so a single cutting plane is able to reveal the detail. So only detailing which can be done over here, you can see wherever there is bending of this cutting plane. So here we can mark a vertical line in this view just to show that this cutting plane is not straight. So there is an offset section into this cutting plane which is going to reveal where it is bending over here. So in this case, through a single cutting plane, so even when the internal geometries they may not lie in a variations, they may not lie in the single line or straight line over there. So wherever the internal cross sections they vary at different cross sections, so single cutting plane through offsetting will facilitate to reveal the true shape or the internal details in a single view over there. So this is the application of the offset section view. So again you can see here we had one hole over here, another hole is at the other cross section, third hole is there at the other cross section. So three lines would have required, three cutting planes would have otherwise required, or three views would be required. But over here in a single view, through the flexibility of bending of the cutting plane, so in a single view we'll be able to see the internal details which are not available in a single straight line. So that is the benefit of using the offset section view. Then the next type of cutting plane is broken section view. You see in many objects there may be internal details which are available either in the vertical direction. Here you can see one internal detail I want to see in the horizontal cross section, another internal detail I can see in the vertical cross section. But if I cut it in a flexible way, now what will happen, I'll be able to see the vertical detail as well as the horizontal detail. So here the flexibility of the cutting plane to be managed in a more efficient manner, so it is going to describe the details of the internal cross sections which are not even available in a single plane. This is available in the vertical plane, this is available in the horizontal plane. So here we are manipulating our cutting plane in such a way that even the different cross sections they are available in different planes, but their details they will be visible in a single view over there. So here you can see another example of this. This is another example. This detail is available in the vertical section, this is available in the horizontal section. So we have manipulated it. Broken means freehand you can just cut it out. So no straight lines are there for the cutting plane, but freehand we have cut it. Just we wanted to show greater internal details which are available otherwise in the different planes as well, or in the different orientations as well. So this is another example of broken out section plane where this detail in this cross section, whereas this detail is there in the horizontal cross section. So this is vertical, this is horizontal cross section. So both of the different cross section or different plane details, they have been shown in a single view. Now the cutting planes, they can be oriented in different ways. That is, here you can have your cutting planes which may be parallel to HP, which may be parallel to VP, which may be inclined to HP, which may be inclined to VP, or which may be perpendicular to both of the HP and VP. So let us see in which orientations we can have our cutting plane. So the first case is that the section plane can be parallel to the horizontal plane and it can be perpendicular to the vertical plane. So just see, this is our horizontal plane, this is our vertical plane. So we can cut open the solid while my cutting plane will be parallel to the horizontal plane. So this is the example you can see, because in this subject we are going to discuss about the traditional solids which are going to be there, maybe prisms, maybe the pyramids, or the circular objects like cone, or you can have the cylinders over there. So all these objects we are going to cut in different orientations and see how their projections they can be obtained on the horizontal plane or on the vertical plane. And we are also required to evaluate the true shape of the cut section into different planes. Now you see, since this is a cutting plane which happens to be parallel to the horizontal plane, so this is our standard solid which is a pentagonal pyramid. So if a pentagonal pyramid is cut with the help of its cutting plane which happens to be parallel to the horizontal plane, so the upper portion of the solid, you see, it is going to be a smaller pyramid. It is a pyramid on a smaller scale because still it is a pyramid. But this portion has been thrown out. This portion we are going to discard, and our main, you see, interest is to develop the true shape of this particular cut section over there. And since this has been cut, this solid has been cut by a cutting plane parallel to the horizontal plane, so the true shape of the cut section will be obtained in the top view onto the horizontal plane, right? So this way, this is the first case that we are going to deal with. So this is the example which we will be discussing in the subsequent lecture. So here we had the pentagonal pyramid. It has been cut by a cutting plane which happens to be parallel to the horizontal plane and perpendicular to the vertical plane. And after cutting, this is the true shape of the cut section which we are required to obtain. So this is the example of cutting plane parallel to the horizontal plane and perpendicular to the vertical plane. So another example you can see, this is a cylinder, right? This is a cylinder, or it can be a pipeline also. So this has been cut by a cutting plane which happens to be parallel to the horizontal plane and perpendicular to the vertical plane. Third example, you see, here we have a square pyramid, right? So the square pyramid has also been cut by a cutting plane which happens to be parallel to the horizontal plane and perpendicular to the vertical plane. Now again you can see, this is this cut section which will be obtained, and its true shape will be obtained on the horizontal plane. Why? Because this cut section happens to be parallel to the horizontal plane. So its true shape will be obtained in the top view onto the horizontal plane. So that's our case number one. Now the second orientation of the cutting plane can be, it is a cutting plane or a section plane which is inclined to the horizontal plane and it is perpendicular to the vertical plane. So this is nothing but this is the auxiliary inclined plane. So usually we will be saying that a solid which may be a prism, which may be a pyramid, which may be a cone, which may be a cylinder, it has been cut by an AIP. The moment we say that it has been cut by an AIP, it means that the solid has been cut by a cutting plane which is perpendicular to the vertical plane, but it is inclined to the horizontal plane at a given angle. And now you see, since the solid has been cut by a cutting plane which is AIP, so this portion we are going to throw out, and the cut surface, whatever cut surface will be there, if you look at that cut surface from the top, its projections obtained on the top view will give us the apparent projections over there. So whatever projections we obtain in the top view, we are going to say that draw the sectioned top view. So whatever section top view we will draw, this section top view will not be the true shape. Why this section top view will not be the true shape? Because the cut section happens to be inclined to the horizontal plane. So since the cut section happens to be inclined to the horizontal plane, so the projections of this cut section on the horizontal plane will be the apparent shape. And what if I have to obtain the true shape of this cut section? I will have to draw an auxiliary plane parallel to this cut section, and then onto that auxiliary plane, just see, this is an auxiliary plane which I am going to draw, and onto the auxiliary plane the true shape of the cut section will be obtained. So one more step will be required besides drawing the front view and the top view of the cut solid over there. So this is again another problem we are going to take up in our subsequent discussions in the next few lectures over there. Now this is another example of this AIP cutting the solid. So this is a pentagonal prism which has been cut by a cutting plane which happens to be perpendicular to VP and inclined to horizontal plane. So its top projections will once again be a shortened one, reduced one, which will be obtained on HP. So its true shape will be obtained if I draw an auxiliary plane parallel to this cut surface, and the projections drawn onto that auxiliary plane will give us the true shape of this cut section. Now this is another example. You can see a cylinder has been cut by a cutting plane which is inclined to horizontal plane and perpendicular to VP. That's why we call it AIP, auxiliary inclined plane. Now this is the problem which I was talking about. So this we are going to discuss in the subsequent lectures over there. So here you can see the view from the top. This is my cut section, and the top view is the sectioned view. It is called section top view, and it is the apparent shape of this cut section. You see, it is a reduced one, an ellipse which is reduced. But if I go parallel to this cut section, now onto this auxiliary plane AIP, I am going to get the true shape of this cut section. So this is the true shape which is bigger than the apparent shape of the top view which has been obtained in the section top view. So this problem we are going to take up in detail in the subsequent lectures. Now the third section plane orientation can be the perpendicular to the horizontal plane and parallel to the vertical plane. So just like in the previous case, section plane used to be parallel to HP. Now here our section plane happens to be parallel to the vertical plane and perpendicular to the horizontal plane. Now the example you can see over here. Here we have an inclined cube over here. Cube is there which is inclined with respect to vertical plane at a certain angle. Now this solid or cube has been cut by a cutting plane which is parallel to the vertical plane, and now this will be the true shape. Why this will be true shape? Because my cutting plane happens to be parallel to VP. If my cutting plane happens to be parallel to VP, so the projections of this cut section, you see this is my cut section over here. So this is the cut section which has been obtained. So the projections of this cut section on the vertical plane, that is in the front view. So just see, on the vertical plane in the cut view, whatever projections will be obtained, so these projections will be called true shape of the cut section. So this is one example of your cutting plane which is parallel to the vertical plane. Now another example you can see, this is a cylinder, hollow cylinder is there. So I have cut this cylinder parallel to the vertical plane. So this portion will be removed. So its true shape will be available, or it will be obtained in the front view onto the vertical plane over there. So this is another representation of a cutting plane which happens to be parallel to the vertical plane and it is perpendicular to the horizontal plane. Now case number 4, a section plane can also be perpendicular to HP and inclined to VP. So this is called AVP. A solid is cut by an AVP means a solid is cut by a cutting plane which is perpendicular to HP. You can see this cutting plane is it is perpendicular to HP and it happens to be inclined to the vertical plane at a certain angle. So let us see the example of this. Here we have a cylinder which has been cut by a cutting plane which is perpendicular to the horizontal plane and it happens to be inclined to the vertical plane. And now you see, since the cutting plane happens to be inclined to the vertical plane, the front view projections which will be obtained over here on the vertical plane and above the XY line, these projections will provide me the apparent shape of this particular cut section. Why the apparent shape? Because this cutting plane is inclined to the vertical plane. So this surface is inclined to the vertical plane. So the projection of the inclined surface on the vertical plane will be reduced view or the apparent view, which is not a true shape. So how do I obtain the true shape of this particular cut section? I will have to draw another AVP which will be parallel to this cut section, either on this side or on this side. And the projections of this cut section onto that auxiliary plane will provide me the true shape of the cut section which is available over here. So just see one example again I am going to show through the question. So this is my cutting plane which happens to be inclined to the vertical plane. This cutting plane is inclined to the cutting plane. And now once I cut this solid, this is a cone, this is cut by a cutting plane. Just see, it is nothing but AVP. AVP stands for a cutting plane which is perpendicular to HP and inclined to VP. Just see, this is inclined to the vertical plane. And whatever projections I got by looking at this cut section in the front view, you see they are shorter one. They are why shorter one? Why do we call them sectioned front view or the apparent view? Because this section, it happens to be inclined to the vertical plane. And since this cut section happens to be inclined to the vertical plane, its projection on the vertical plane in the front view will provide us the shortened view or the reduced view. So what if we want to obtain the true shape of this cut section? So we have to go parallel to this. This is my again AVP, another AVP we have drawn which will be parallel to this cutting plane. And since this cutting plane is parallel to this, or in other words, my cut section is parallel to this AVP, the view obtained of this cut section onto this AVP will provide me the true shape. Now you can see this is a bigger picture as compared to this one. So this is a section front view, whereas this is my true shape of the cut section. So this is case number 4. Next one, I have another orientation of the cutting plane which happens to be perpendicular to both the horizontal plane and the vertical plane. So just see, here I have my cutting plane which is perpendicular to both the HP and VP. So obviously this will be parallel to the profile plane. So if it is parallel to the profile plane, the cut section true shape will be available in the profile plane. Otherwise, in the front view, the cut section will be available as a horizontal line or the edge view. Similarly, if you look at this cut section from the top, its projection on the horizontal plane will again be an edge view over there. So neither in the front view on the VP nor in the top view which is obtained on HP will give me the true shape of the cut section. So only the profile plane which is parallel to this cut section will provide me the true shape of this cut section. Here you can see, here again I have a cylinder or an object. If I am going to cut it parallel to X1, Y1, so X1, Y1 is my profile plane which will be located over here. This is going to be my profile plane. So this profile plane will be parallel to this particular cutting plane. So just check, the cutting plane happens to be parallel to the profile plane. So what this portion will throw out or discard once again. So whatever internal detail of this component will be obtained on the profile plane, this will be the true shape. Just check this out. So here I have a solid which is pentagonal pyramid. I have cut this solid parallel to the X1, Y1. Just see, by the profile plane. So the view obtained on the profile plane will give me the true shape of this particular solid over there. So this is another example of section plane being perpendicular to both the horizontal plane as well as the vertical plane. Now we are going to look upon the theory of the sectioning. That is, whenever a section plane cuts a solid, it intersects or coincides with the edges of the solids over there, which can be the vertical slant edges, it can be the base edge, it can be the corners. So the cutting plane is going to cut the solid, and we are going to view the cut portion through the intersection of this cutting plane with the various edges of the solid. And this point of intersection of the section plane with the edge of the solid, it is called point of intersection. So in whichever points my section plane is going to intersect and cut the vertical edges or the slant edges or the base edges of the solid, all those points, they will be called as, or they will be termed as, points of intersection. And for the polyhedra, that is the solids which are having the straight edges, which are bound by the straight edges, the true shape of the section will depend upon number of points of intersection. So I have shown you number of examples. The solids have been cut by the cutting plane, and wherever different points of intersections have been obtained after cutting, so those points of intersections have been projected further to reveal the sectioned top view or the apparent view, or even the true shape or the auxiliary views of the cut sections of the solids. So the shape of section will be a polygon of the sides equal to the number of points of intersection. That is, this is applicable for the polyhedra. So in case of polyhedra, let us say n number of points of intersections are there. So my section top view will be showing me n number of POIs, which may give me the apparent shape or which may give me the true shape, depending upon the orientation of the cutting plane with respect to the solid. But I am going to get the straight edges which are going to be joined by these POIs to give me the true shape of the cut section over there. A cutting plane will cut at a minimum of 3 edges in case of a polyhedra. This we have seen in the case of a triangular pyramid. In case of triangular pyramid, minimum of 3 corners or 3 edges will be generated after the cutting of the polyhedra with the cutting plane. So minimum 3 POIs could be there, but the number of maximum points of intersections depend upon the nature of the polyhedra, that is prism or the pyramid, and also the angle of inclination or the orientation of the cutting plane with respect to your reference planes over there. So here you can see, in case of prisms or in case of cubes, you can have the maximum number of POIs will be, usually the number of POIs, they are equal to number of the base edges over there usually. But maximum number of POIs that you can have once a prism or a cube has been cut by a cutting plane, it can be n plus 2. So usually you in 80% or 85% of the cases, number of POIs will be equal to the number of base edges, 85%. But in 10 to 15% cases, maximum number of POIs can be n plus 1 or it can be n plus 2. I will be showing you with the help of the examples how we can obtain larger number of POIs compared to the number of sides of the base over there. So in case of prism or cube, it can be maximum to be n plus 2. You can have n, you can have n plus 1, or you can have n plus 2. Whereas in case of pyramids or tetrahedrons, the number of POIs usually, otherwise they will be 85% of the cases they will be equal to n, which is equal to number of sides of the base. But in 15% of the cases you can have n plus 1. So here you don't have n plus 2. So there is only n plus 1. I'll also explain why you have only n plus 1 and why you have n plus 2 over here, right? So we must remember that maximum number of points in which a cutting plane can cut a solid. In case of prism and cube, they can be n plus 2. In case of pyramids, they can be n plus 1 maximum. So here you can see, as I have told you, in 85% of the cases or even 90% of the cases, the cutting plane is going to pass through all the vertical generators basically. Just see, these are the vertical slant edges of the pyramid. Just see, this is a hexagonal. Again, this is a hexagonal pyramid. This is a square pyramid. This is a triangular pyramid. You can see number of base edges are 3. Points of intersection, they are cutting the slant edges of the pyramid. So if my pyramid is cut through and through, you see, through the slant edges, so the number of points of intersection, they will be equal to number of edges or the corners of the base. So number of edges of the base, they were 4. POIs, they are also 4. Here number of edges of the base, they are 6. So again POI, point 1 of intersection, point 2, point 3, point 4, point 5, point 6. Again they are 6 over here. Here there are 3. Let us talk about the prism. This is again a pentagonal prism. So prism is cut through and through. So all the longer vertical edges, so they have been cut. So once all the edges they have been cut, the prism has been cut through and through. Maybe the orientation is inclined. It could have been flat also. Still 5 POIs would have been obtained. So in 85 to 90% of the cases, your POIs, they are usually equal to number of edges of the base. Then how do we obtain n plus 2 and n plus 1? So let us look at those examples. Just see, this is my square prism over there, but this square prism is not cut. You see, I'll give you another example. If this square prism had been cut like this, so I would have obtained 4 POI. That is, it is cutting my solid through and through. It is cutting my solid through and through, and all the vertical generators have been cut. So 4 POIs would have been obtained. But if my cutting plane is oriented in such a way that it cuts, you can see n minus 1 edges. One edge is cut, second edge is cut, third edge which is lying behind, that has also been cut. But this fourth edge has not been cut. So since this fourth edge has not been cut, but it is cutting the top surface over there instead of the fourth edge. So cutting the top surface means that you can see it is cutting this edge, it is cutting this edge, it is cutting this edge. So had it cut all the edges, it would have cut A1 also. But it is cutting the top surface over there rather than one edge. So if it is cutting top surface, you see which portions it is cutting. It is cutting 1, 4. It is also cutting 1, 2. So had it been cutting the vertical longer edge, only 4 POIs would have been obtained. But now it is cutting 3 vertical edges, but it is cutting, might have cut either of the base also. So it is cutting either the top or the base. If it is cutting the top face only, you get n plus 1. If it is cutting even the base over there, you would have got n plus 2. So in that case, it would have cut 2 edges and 2 surfaces. One surface on the bottom and one surface on the top. So then you would have got 6 points instead of 4 over there. That example also I will be showing. So n plus 1 will be there in case of prisms when my cutting plane is cutting n minus 1 vertical edges and it is cutting either the top surface or it is cutting either the bottom surface. So if it is cutting either the bottom surface, so rather than 1, 2 points would be created. If it is cutting top surface, once again 2 points will be created at the top over there. So that is why we can see 3 edges have been cut over here and 2 surfaces of the top surface have been cut by this cutting plane. So that is why n plus 1 cutting edges have been obtained in the case of a prism. Now this is another example of a prism where my cutting plane is oriented in such a way that it is cutting top surface. You can see it is cutting top surface as well. It is cutting bottom surface as well. Please check. It is cutting bottom surface as well. It is cutting top surface and it is also passing through 2 of the vertical edges. So now 2 of vertical edges, they are uncut. This edge is also uncut.
this edge is also uncut, but instead of cutting these two edges, one surface of the top face has been cut. So one surface of the top face means 3 4 has been cut and 1 4 has been cut. So rather than one edge, now you have got two POIs over there. Similarly, this vertical edge has not been cut over here. So instead of cutting this one vertical edge, now my cutting plane is cutting two edges of the base basically. So two POIs will be obtained corresponding to AB and BC. So even though my cutting plane is cutting only two vertical edges, but since it is cutting top face as well as the bottom face, so the 2 points corresponding to the bottom face, 2 points corresponding to the top face, and 2 points corresponding to the two vertical edges. So even though the base edges were 4, I have obtained 6 POIs in this case. So n plus 2 in case of a prism has been obtained. So this is one example which we will be discussing in detail in the subsequent lectures. Then in case of pyramid, once again, my cutting plane is cutting, just see, this is a square pyramid. So usually had it been cutting all the slant generators, 4 POIs would have been obtained. I am cutting it like this, just see. I am cutting this pyramid over here, 4 cutting points they are generated. But if I am going to cut only 3 slant edges over here, but my cutting plane does not cut the 4th generator or the 4th slant edge over here. It rather instead it cuts my base. So if my cutting plane passes through the base, now it will be cutting 2 edges of the base over there. So that is why 3 POIs are there corresponding to the vertical slant edges which have been cut, and 2 POIs have been there corresponding to the base. So n plus 1 POIs have been obtained. So why in pyramid you don't have n plus 2? Because there is no top surface in case of a pyramid. So in pyramid you don't have the top face. Had you got top face over there, that would have led to the prism over there. So in case of pyramid, since you have only one face, so one face can be cut at only 2 points. So 3 for this and 2 for this. That makes it n plus 1. So you can check. This is again a hexagonal pyramid. So in a hexagonal pyramid, 6 slant edges are there. So my cutting plane is oriented such that it does not cut the 6 slant edge over here. So 5 slant edges they have been cut, and then one the base. So once it cuts the base, you can see AF has been cut, AB has been cut. So 2 edges of the base have been cut over here. So since 2 edges of the base have been cut, so n plus 1 number of POIs have been generated. So you can see instead of 6 points, I am able to obtain 7 POIs over here. 11, 12, 13, 14, 15, 16, 17. So 7 POIs have been generated in case of the pyramids over here. So here again you can check that this is again a 3D representation of a hexagonal pyramid being cut. So one edge is untouched, whereas the other 5 edges they have been cut by this cutting plane. But since it passes through the base, so passing this cutting edge passing through the base leads you with 2 POIs. So 1 POI has been missed, but 2 POIs have been added. So 5 plus 2, 7 POIs have been shown into this 3D view which we have drawn. Now we have understood by now that the section will show its true shape when it will be viewed in the normal direction. That is, whenever you want to obtain the true shape of any particular cut section, you have to go perpendicular to it. That is, you have to look at it from perpendicular direction. So your plane of projection should be parallel to the cut section over there. So obviously, to find out the true shape of a section, it must be projected on a plane parallel to the section plane over there. So we have to project our cut section on a plane which will be parallel to the section plane. So in case of solids having the curved surfaces, that is cylinder, cone and sphere, so POIs they are located between the cutting plane and the lateral lines. What are these lateral lines? These are the generators or the artificial generators into which we are going to divide our cone or a cylinder, because we have already discussed while we were discussing the projections of the solid. In case of cone and cylinder or a sphere, you have the flexibility. You can divide your cone or a cylinder in 8 equal parts or 12 equal parts. If you are making a construction with 12 equal parts, so 12 POIs you are going to get. If you are going to divide your circle or top view of the cylinder or a cone into 8 equal parts, so 8 POIs you are going to get over there. So in order to draw the true shape in case of a cone or a sphere or a cylinder, circular portions will be drawn. That is, freehand circular ellipse or a circle will be drawn over there. Whereas in case of the polyhedra, the POIs will be joined by the straight lines. So the true shape of a section of a sphere is always a cylinder, sorry, always a circle. This thing we should remember. You cut a sphere in any orientation, the true shape of the cut section will always be a circle. And this thing I have already told you, that sections of prisms and pyramids, they will be joined by straight line segments, whereas the sections of cylinders and cone, they will have the smooth curves over there. Now you can see, if we are going to cut a cylinder or a cone in different ways, the resultant shapes, they are going to be different. If we have a cylinder available with us and we are going to cut the cylinder perpendicular to the axis, obviously the true shape of the cut section will be a circle, right? Then if we cut a cylinder inclined to the axis, cutting through all the generators, then the true shape which will be obtained will be an ellipse. Again, one problem we are going to discuss related to this also, this case as well. Whenever a cylinder is cut by a cutting plane parallel to its axis, the resultant true shape will be a rectangle over there. Similarly, if you cut a cone with respect to the axis at different orientations, these are the standard shapes which you are going to get. So we are going to discuss these shapes in detail in a while. That is, when you cut a cone perpendicular to the axis, that is parallel to the base, you get the true shape as the circle. If you cut a cone inclined to the axis, cutting all through all the generators, you get the true shape as an ellipse. This we have already seen. This also we have seen. Third, if we cut a cone parallel to a generator, the true shape of a cut section will be a parabola. If I cut a cone inclined to and one side of the axis, we get the construction as the hyperbola. And if we cut a cone parallel to the axis, the resultant the resultant true shape of the cut section will be a rectangular hyperbola. So let us look at all these cases one by one. So case number 1, here you have a cone over here. We are going to cut this cone in different ways, and whatever different cross sections are obtained, they are called conic section. So the sections obtained by cutting the cone in different positions relative to the axis, they are called conic section. And these are 8 or 12 generators which we can get depending upon whether we have divided our circle or a cone or a cylinder into 8 equal parts or 12 equal parts. Accordingly, that many number of generators will be possible over there. Now you see, this is cutting of the cone parallel to the base. So whenever you cut the cone parallel to the base or perpendicular to the axis, just see, this is the axis. We are cutting the cone perpendicular to the axis. So the resultant true shape of the cut section will be a circle, and this will be available in the top view. Next, if the cutting plane cuts the cone inclined to the base and it passes through all the generators, the resultant true shape of the cut section, it is an ellipse. So this we have already seen in our previous discussion in this lecture. That is one question also in tutorial we are going to see in the subsequent discussions in the next lectures over there. So the true shape of the cut section will be an ellipse over there. And obviously it won't be obtained in the top view. It will be obtained on an AIP which will be parallel to this particular cutting plane or the cut section over there. So this will be your true shape. Third, whenever you cut a cone parallel to one of its slant edges, just see, this is my cutting plane, this is my external slant edge, this is my external slant edge. You can cut it this way, you can cut it this way, but this cutting plane has to be parallel to the slant edge. So then the resultant shape of the cut section will be a parabola. This is again a geometrical shape which can be verified mathematically as well. So again you can see this is a freehand curve which you are required to draw. But once again, true shape will not be available in the front view. It will be available on an AIP which will be drawn parallel to this cut section over here. Right? Next one, when the cutting plane cuts the cone at a small angle to the axis. Now it's not parallel, just see, it's not parallel to generator, it is at a small angle to the axis. Then the true shape of the cut section, it will be called a hyperbola. That is another geometrical shape which is generated over there. Next, whenever a cutting plane cuts a cone parallel to the axis, now you see earlier it was parallel to the slant edge, now it is parallel to the axis. If our cutting plane happens to be parallel to the vertical plane, please check, our cutting plane happens to be parallel to the vertical plane, then the true shape of the cut section will be obtained on the vertical plane. No additional AIP or AVP will be required. So straight away on the vertical plane, this is the shape which will be generated. And the name of this shape is rectangular hyperbola. So this is again a geometrical shape which can be verified mathematically as well. Again, it's a freehand curve which we are required to draw over here. Next, we can divide the cut solids into two different categories depending upon whether the cutting plane happens to be parallel to the base or the cutting plane happens to be inclined to the base. Again I repeat, we can classify the cut solids into two parts, two categories depending upon whether the cutting plane happens to be parallel to the base or it happens to be inclined to the base. So please see, whenever a cone or a pyramid, it is cut by a cutting plane which is parallel to the base, so the upper portion we throw it off. Upper portion will be again a smaller cone, it will be smaller square pyramid, it will be smaller hexagonal pyramid. So initially it was a bigger pyramid, bigger cone. If I cut it parallel to the base, the solid which is thrown out, which is discarded, will be a smaller shape of the original shape. So this will be smaller cone, this will be smaller square pyramid, this will be smaller hexagonal pyramid. So that is thrown out. So removing the apex, so apex portion we are going to remove or throw out or discard. So the remaining solid, it is called frustum of the cone or frustum of the pyramid. So these are the images of the frustum of the solid whenever a solid is cut parallel to the base. And the second category of the cut solids is truncated solid. So whenever a solid is cut by a cutting plane which is inclined to its base, so whenever a solid is cut by a cutting plane inclined to its base, then once again upper portion we are going to throw off, apex portion will be thrown off, but the remainder solid is called truncated solid. So this is truncated prism, pentagonal, truncated cylinder is there, truncated triangular pyramid, this is truncated cone, this is truncated hexagonal pyramid is there. Now next, whenever we cut a solid, now the cut portion will be shown with the help of the hatching lines. So hatching lines are 2H lines which are drawn at an angle of 45 degree with respect to the intermediate XY reference line. So these are the equispaced lines which will be drawn just to show that this portion of the solid has been cut by a cutting plane. So this is called hatching over there. This is called hatching. The portion of the solid which has been cut with the help of these hatching lines. So the cut portion or the section portion of the solid will be represented with the help of these hatching lines over there. And
these hatching lines, they are drawn at an angle of 45 degree to the intermediate principal planes over there, or the lines of symmetry of the section over there. And the spacing between the hatching lines, it has to be uniform all through. You should not draw the hatching line that few hatching lines are closer to each other and the other ones they are having larger distance in between them. So you should have the uniform spacing between all the hatching lines in any given case. Now, even though in our engineering drawing we are going to show the hatching lines as the ones which are inclined at an angle of 45 degree, but usually we assume that all the models of the solids we have picked up, they are belonging to the metals category. But if in practical, that is in the technical drawing, if we are cutting open different types of the materials, different types of the objects over there, so depending upon their applications, these are different types of the hatching which are recommended in different situations. That is, in industry if we have to use it, then if we are carrying out these types of hatching, it means we are talking about the metals over there. Then for lead and zinc and tin and white metal, the hatching done will be of this type. For the glass, because of its amorphous structure over there, the structure gives us the hatching like this. If it is a packing or the insulation material like porcelain, stoneware, marble or the slate, then this is the pattern of the hatching which should be done. Again, for the insulation materials like asbestos, fiber, felt, synthetic resin products, again depending upon the nature of the material, we have changed the hatching pattern. Similarly, this is the hatching pattern for the stack lamination. For concrete, it is very easy to understand. Concrete has got sand, particles and the pebbles over there. So we are mixing both of them up. So any structure which is section that is related to civil engineering, there may be a beam, there may be a column over there which is made out of concrete. So there this sort of hatching will be done. Similarly, wood. So wood is having again fibrous structures. So just to show the fibrous nature of the wood, we have got the hatching pattern over here. Similarly, some sort of a liquid tank, if we are going to section, just to show what is the level of the liquid over there. Then for the liquid, you can see this is the nature of the liquid. So that is how the nature of sectioning will also change. So this is how you see in industry or in technical drawing, depending upon the nature of the object or material which has been sectioned, we are going to use different procedures for sectioning. But over here in engineering drawing, we are going to assume that all the materials, they are all the solids that we are going to section, they belong to this category, that is metals category. So this sort of sectioning will be carried out in all the sectioning of the solids over there. So this is all about the introduction which is related to the sections of the solid. So here we have discussed about different types of the orientations of the cutting planes which will be there while you are going to cut the solids, how cutting of the solids in different orientations, they yield you with the true shape of the cut section. And then we have also discussed how we can obtain different types of points of intersections when we are cutting the solids in different orientations over there. So this was all about the basic introduction to the section of the solids. Now we are going to proceed to problems related to the sections of the solids, and then one by one we are going to pick up different problems in our subsequent lectures. So thank you very much. Thanks.